Hey guys, so today we've built for you guys an accelerometer. So you can actually see that being put together in the background right here. And we're just going to talk to you guys about the mathematics behind it, how we chose the certain design that we did, and if we were to do it again, how we would change that design. So as you can see, that's me, that's the motor working, and when you put it into the system, you have a working accelerometer. So yeah, our goal was to be above 1G of force, and Walter's now going to talk to you guys about the math behind the accelerometer that we made.
For our design, we chose a wheel connected to or with a peg. This wheel would rotate around its axis thanks to the motor, causing the peg to have rotational motion. And in order to translate the peg's rotational motion, thanks to the motor, into motion in one axis, in one direction, one-dimensional motion, we created this structure that would connect to the peg. And as the peg rotates, this structure would only capture the peg's displacement and position in the x direction due to the way the forces work. Therefore, this allowed us to capture and translate the rotational motion of the motor into one directional motion in the x direction, therefore causing a lot of acceleration and velocity changes with our structure. Thanks to the system we chose, and with the peg being about a distance r from the center, the force that is applied from the peg onto the structure that we chose is only in the x direction, meaning that the structure only changes position in the x direction because the force and the acceleration placed from the peg onto the structure is only in the uniform one-dimensional x direction, correct? Therefore, in order to find the position of the peg, and in turn the same position of the structure and of the rod, we use the equation x equals r cosine theta. However, in this case, theta is equal to the angular velocity, or the rotational velocity, times the time. Therefore, we plug that in, x equals r cosine wt theta, or wt, sorry, excuse me. And in order to find the acceleration, which is ultimately what we're trying to solve for, and then ensure that we set equal to more than or equal to 1g, 9.8 meters per second squared, we derivate the position formula for the position of the peg and the structure in the x direction. We find the velocity, and then we take the derivative again in order to find the acceleration. Once we have found the acceleration equation, we understand that this value, cosine of wt, will translate and will just alternate between 0 and 1. Therefore, in order to get our maximum acceleration, which is what we're trying to solve for, we have to maximize the value attained from w squared times r. Therefore, we have two factors that we can control in order to get the acceleration to equal 10 meters per second squared, which is what we decided to try to shoot for when determining how to calculate and what to change in order to get W and R. As you can see here, the omega squared R in the acceleration times graph alternates, and the maximum acceleration is here at the peaks, both in the positive and in the negative acceleration due to the variation in the movement of this structure. Therefore, we have to find how to maximize and the values for omega and r that will let us make these peaks equal to 10 meters per second or greater. In order to find the maximum acceleration that our system would produce in the x direction, we committed to finding the omega in radians per second by measuring the amount of times that the engine would spin. So measuring the amount of revolutions per minute that the wheel had based on our motor selection, which was motor B. Therefore, being able to find the revolutions per minute and averaging various tests out in order to find the most accurate value, we were able to transition that into radians per second and then plug it into the equation in order to find our optimal r to give us the acceleration that we required. In order to find omega, we did 15 trials measuring the amount of revolutions that the wheel had per minute, and then converting it to revolutions per second. We averaged the result of all 15 trials in order to get the most accurate result. And then we multiplied the value of revolutions per second by 2 pi in order to transition onto radians per second. And our final result was 13.36 radians per second. Once we found that, we come over here and we plug it into our acceleration equation, plugging in 10 meters per second for the acceleration, 13.36 radians per second here, and then as well as here, and solving for our R. After plugging in 13.36 for omega squared, and plugging in 10 for 10 meters per second for the acceleration required in order to find the radius that we need in order to achieve this acceleration, we got 0.056 meters, and then when converting that to centimeters, the radius, meaning the distance from the center of our disc rotating with the motor to the peg that will be converting its change in position, its displacement in the x direction, to the structure. That distance must be 5.6 centimeters in order to achieve the desired acceleration. In our process to solve for the radius required in order to get an acceleration of equal to or greater than 9.8 meters per second squared, we should have included the friction of the supports in our consideration and in our force analysis of solving for the acceleration. So we should have included the force of friction, which is equal to the normal force of just this horizontal structure, the structure that moves in the x direction, just that one, times the mu, which is the force of friction between acrylic and acrylic, and then set it equal to the acceleration due to friction.
So here's a visual of a snippet of the number of G's calculated by the accelerometer. This was calculated using an Arduino code, and you'll notice that the outer points, for the most part, are around either +1 or -1 G, depending on the direction of the motion. And so we found that for the most part, our values were close to our predicted values. However, there can be some deviation in why our calculations were slightly off. Sometimes it would reach up to 1.4 Gs, for example. One reason could be that the screw didn't perfectly fit in the structure, which could result in a bit of swinging and a bit more vertical movement than horizontal, which would change the amount of movement of the structure. Also, just the fact that the way that we calculated with the Arduino, we actually attached a sensor to the very end of the portion that moves horizontally, and so the fact that it wasn't closer to the center, there's potential that the results could have been slightly skewed. If we were to do this assignment again, there's a couple things we would definitely do to improve it. The first would be, as Walter had mentioned, calculating the friction and calculating the wheel size and potentially having a different wheel size that would result in better results. The other main one would be to ensure that the system itself was stable, so that there was no vertical movement when the engine was on. There was a tiny bit of vertical movement that could have changed the results. But other than that, we were actually really happy with our results, and we feel like we did a good job in being able to get what we desired. So thank you very much, and have a good one.